remainder theorem for polynomials. So I'm going to assume first that we have some functions or even some expression where your numerator, so I designated this numerator n of x, and then we have our denominator d of x. So both of these are polynomials, but moreover, I will assume that d of x has this particular form. So it's basically of order 1, and it is of this form. So x minus some k, where some k is a number which can be a real number of any kind that we like. Now, the idea behind the remainder theorem is tied into the long division for polynomials. So when you're doing long division, so I'm going to give you an example here. Let's say I have 3x squared minus 4x, say plus 3, and then, so that would have been my n of x, okay, so that's in the numerator, and then I'm going to try to keep it in this particular form, so let's say x, and I'm going to keep this, let's say, plus 2. Now, you might say, well, isn't it supposed to be x minus k? Well, so this you can, of course, rewrite as x minus that, which is going to give you the x plus 2, and that would have been your k right here, which is your negative 2. So it doesn't matter. So this right here, if it's positive or negative, is irrelevant to us, so it can be either one or the other. The thing that I want you to keep in mind is if you had to do long division for this, now if you forgot about long division, you can check out, I'll put up a link up above there for polynomials. You would have to do actually quite a bit of work to try to see how this long division pans out. Now I'm going to do the long division right here because I want to kind of show you something with regards to this remainder theorem and then kind of tell you what that is. So let's say I'm going to try to do long division right here. So I'm going to line everything up as we have it right this. Now I am of order 1 right here, so that makes my life a lot easier. Okay, so let's try to get started. So now for long division, so I want to get rid of this term right here. And to do that, I'm going to, I guess, take 3x multiplied by x plus 2, which is going to give me 3x squared plus 6x divided by, I'm going to subtract, so that is gone. Then this is going to give me, I guess, this annoying negative 10x right here. I'll bring this down. So bringing this plus 3 down. Now to get rid of this negative 10x, I guess I can multiply by negative 10. So that factor, and that's going to give me negative 10x minus 20 divided by, so again, so subtracting, so these are gone, and I'm going to get 23. And this turns out to be my remainder in that long division, which you can do. Now, that's quite a bit of work. And here, what I want to show you is, and that's what the remainder theorem states, it does make this assumption right here that our denominator is like that. So it's basically for a special kind of denominators. But instead of doing all of this work, if you wanted to find this remainder only, so if that's the only thing that you wanted to find, so you weren't really interested in trying to get the quotient here, you were just trying to see if what the remainder is, it turns out that instead of doing this long division, you can do this much simpler. And to do that, the remainder theorem states is that all you have to do is you have to substitute, okay, into your numerator the 0, okay, of this denominator. So we know that, so for instance, x, okay, so here if you were solving this, it would have been equal to negative 2, and that's coming from x plus 2 equals to 0. So if we wanted to find that 0, we know that that would have been the restriction that we would have to put if this was a function, for instance. Now, The remainder theorem states that if you take your 0 and you substitute it into your numerator, you will obtain this remainder. So instead of doing the entire long division to find the remainder, all you have to do is substitute your 0 from the denominator into your numerator. So in this case, it's going to be this. I'm going to substitute it in, and the result is your remainder. And that's pretty neat, and it saves us time in case we want to be able to just find the remainder. Well, let's try it just and see what it will actually give us. So this is going to be, so 3 times, this is negative 2 squared, so that's 4. So this is going to be 12 plus 8 and then plus 3. And as you can see, this gives us 23, which is exactly the remainder we found through that long division. So you might say, oh, that's pretty neat. And definitely this is much easier to do than the actual long division for polynomials. Now, where is this handy, this remainder theorem? Well, it's actually really handy to try to see if your denominator, where it is in the form of x minus k, or x, plus or minus some number, if it is a factor of the numerator. So here our remainder was 23. So we know what this tells us is that x basically plus 2 is not a factor of that numerator. So it doesn't go into it. But if our remainder turned out to be 0, so if we substituted it back in and we got 0, meaning there was no remainder, what does that tell us? If there is no remainder, that means that the denominator is a factor of the numerator. And that is super useful if, for instance, you wanted to be able to see what the factors are of the numerator. Okay? So let's take a look at a few examples and apply this remainder theorem. So now we have here a few examples. So there's basically 4 examples. So let's try to apply the remainder theorem to these examples and then see what happens. So instead of going through the whole process of kind of long division or any division that you might apply, let us just simply take the 0 of the actual denominator and then substitute it back in to see what the remainder will be. Now, one key thing to remember, so please don't forget that these denominators do have to be of first degree, or first order that you have. So you can't have quadratics or anything which is higher. So we're just kind of have simple denominators in this case. So in the first example, I'm going to copy this down. Copy this, bring it down. And now I do want this, in the form of x minus k. So basically, I'm trying to find the 0, which is going to be just -1. And now I'm going to take this -1 and I'm going to substitute this back in here to see what the remainder would be. And substituting that in, I would get 4. So -1 cubed plus 2 times -1 minus 7. And then I can go ahead and compute it. So what would that be? Well, I guess I'm going to have -4 minus 2 and minus 7. So that's going to be -6. So I guess that's -13. So that would have been my remainder if I was going to go through the whole process of the division. And now I'm going to just do the division for you. I'll do it in fast forward fashion just so that you can see that indeed this is the denominator. All right, so there you have it. So that's the process of the division. I did it in long division within this one, and you notice that indeed, okay, so that is the remainder. So let's take a look at another example. So I'll take a look at the second example. So this one right here. Let's copy it. Let's bring it down. This one is already in our form that we wanted. So our 0 right here is basically 1. So we're going to substitute 1 right here and see what happens. And that will give me, and that's 1 plus 1 plus 3, that's 5, minus this gives me 0. So the remainder here is 0. And I'm not going to do the long division again or the division to show you that, but I do want to talk about, okay, so what does this exactly mean? Well, remember, if the remainder is 0, so what that would tell us is that this basically is a factor of the numerator, which is a great tool that we can use, and typically this is kind of called the factor theorem, where you can check for yourself if a factor can be applied into a particular polynomial. So in this case, we were doing division, but if you were asking the question, is x minus 1 a factor of x cubed plus x squared plus 3x minus 5, which is that numerator, then the answer is yes, and that is actually shown to us by the remainder theorem. So that's pretty neat to be able to have that tool in our toolbox if we ever do need to see if kind of a first order is a factor of a particular polynomial. So that's another example. So this one actually wouldn't have any remainders, it would go right into it. Let's take a look at a third example, and hopefully, you know, by now you should be able to kind of tell. Okay, so how the remainder theorem actually works. So here, this doesn't exactly look like we would like it to, and so, you know, it's not just x minus something, but again, so it is of first order, so let's, you know, work this out, and this would have been, I guess, just 3 over 2. So that's the 0 that we would have of this, and this is what we would have to substitute in here. And now if we do substitute in here, we're going to try to find what the remainder for that is. And that would be, so I'm going to do it in, I guess, fast forward fashion. All right, so there you have it. Okay, so this would have been the remainder. So that means that this definitely is not a factor of the numerator that we would have in there. So that's the remainder that we would carry out. Now let's do a final example. Paste, and again, so here, you know, we have to rearrange this. Okay, so to try to get our 0, it's going to be minus 3 over 2. That's the 0 of that, and then we can plug this back in here. Now this one is looks like it's going to be pretty painful, but let's see what happens. I'll try to plug it in and do it in fast forward fashion. All right, so there you have it. So basically the remainder here is 0. So what does that tell us? It actually tells us that this 2x plus 3 is a factor of the numerator right there, which is pretty neat if you actually went ahead and tried to do this throughout. Now, just to make sure, I will do the long division for this one, and I'll also do it in fast forward fashion, because I don't want you to think, so just because this is 2x plus 3, you know, that it doesn't actually work. So let me do the long division, and then we're going to compare and then see that we should get a remainder of 0. All right? All right, so there you have it. I kind of did all the steps just so in case you wanted to see it or screenshot it, try it for yourself. So notice indeed the remainder here is 0. So it's pretty useful to have this remainder theorem, and I guess it also allows us to find when we have a factor of a polynomial, because if the remainder is 0, then we know that it's going to be a factor of that particular polynomial, which is kind of useful. All right, so that's all that I'm going to say this, and I hope that you're able to use this to your advantage instead of doing the long divisions, in case you ever wanted to find out what the remainders are, or if a particular first order polynomial is a factor of another polynomial. Okay, thanks for watching. See you in a future video. Bye.